The flickering flame dances behind glass, casting long shadows across cobblestone streets. A lamplighter makes his rounds through the fog-laden avenues of Victorian London, his long pole reaching up to ignite each fixture one by one. The year is 1853, and the world is changing faster than any generation before has ever witnessed. These lamps, now the subject of countless theories about lost technology and hidden power sources, stand as silent witnesses to an age of remarkable innovation. But what do they truly represent? The answer lies not in mysterious energy or forgotten civilizations, but in the extraordinary ingenuity of 19th-century engineers who pushed the boundaries of what combustion science could achieve. The gas lamp era began not with a single eureka moment, but through decades of careful experimentation. In 1792, a Scottish engineer named William Murdoch conducted early experiments with coal gas in his home in Redruth, Cornwall. He discovered that heating coal in an enclosed container produced a flammable gas that could be captured and burned to produce light. This was not magic. This was chemistry. The process involved heating bituminous coal in the absence of air, releasing volatile compounds that could be channeled through pipes and ignited at controlled points. Murdoch understood the science behind his discovery, and he spent years refining it before demonstrating its practical applications. The coal itself held secrets that generations of chemists worked to unlock. When heated in sealed retorts, bituminous coal released a complex mixture of gases including hydrogen, methane, carbon monoxide, and various hydrocarbons. Each of these components burned with different characteristics. Hydrogen produced a hot but relatively dim flame. Methane burned brighter but required careful mixing with air. The art of gas production lay in controlling this mixture to achieve optimal illumination while minimizing unpleasant odors and dangerous byproducts. This required sophisticated understanding of chemical processes that developed gradually throughout the early 19th century. By 1812, London saw its first gaslit street. The Westminster Bridge glowed with an otherworldly brilliance that amazed pedestrians and carriage drivers alike. People gathered to stare at these new fixtures, marveling at light that seemed to appear without visible fuel. But the fuel was there, hidden beneath the streets in a growing network of iron pipes. The Gas, Light and Coke Company had been established, and with it came the infrastructure that would transform urban life. This was engineering on a massive scale, requiring metallurgists, pipe fitters, surveyors, and chemists to work in coordination toward a common goal. The challenges of building this infrastructure were immense. Iron pipes had to be cast with enough precision to prevent leaks yet remain affordable for installation across entire cities. Joints between pipe sections required careful sealing with materials that could withstand both the chemical properties of coal gas and the physical stresses of burial underground. Workers developed techniques for excavating streets, laying pipes, and restoring surfaces with minimal disruption to commerce and daily life. The organizational complexity rivaled any modern construction project, requiring planning documents, supply chains, and skilled labor forces. The lamps themselves were designed with precision that modern observers sometimes mistake for something more exotic. The burner tips were carefully calibrated to mix gas with air in exact proportions, creating a flame that was both bright and efficient. The Argand burner, invented by M. Argand in 1780, introduced a hollow circular wick that allowed air to flow through its center, dramatically increasing the amount of oxygen available for combustion. This simple innovation multiplied the brightness of oil lamps by a factor of 10. The same principle was later adapted for gas lighting, producing flames of remarkable intensity that seemed almost miraculous to first-time observers. The physics behind this improvement were straightforward but required insight to discover. Combustion depends on oxygen reaching the fuel. A solid wick burning oil or a simple jet of gas can only access oxygen from its outer surface. By creating a hollow cylinder of flame, the Argand design exposed both inner and outer surfaces to air. This effectively doubled the combustion zone and dramatically increased light output. Understanding this principle required no advanced theoretical physics, only careful observation and willingness to experiment with different designs. Some who encounter photographs of ornate 19th-century light fixtures assume they must have operated on principles unknown to modern science. The elaborate metalwork, the crystal globes, the sheer elegance of these designs suggests a sophistication that seems at odds with the supposedly primitive technology of the era. But this assumption reveals more about modern misconceptions than about historical reality. The Victorians were not primitive. They were experimenters, tinkerers, and visionaries who understood physics and chemistry at levels that allowed them to create genuinely impressive devices. Their education systems produced engineers capable of complex calculations and practical problem-solving. Consider the Welsbach mantle, patented in 1885 by Austrian chemist Karl Auer von Welsbach. This invention transformed gas lighting from merely functional to truly spectacular. The mantle was a mesh of rare earth oxides, primarily thorium and cerium, that glowed with intense white light when heated by a gas flame. The science behind this phenomenon is called incandescence. When certain materials are heated to high temperatures, they emit light across a broad spectrum. The specific compounds Welsbach used happened to produce light that closely mimicked natural daylight. There was nothing mysterious about this. It was the application of careful research into material properties conducted over years of laboratory work. Welsbach did not stumble upon this discovery by accident. He was a trained chemist who had studied the properties of rare earth elements extensively. His research led him to understand that certain oxide combinations produced particularly bright incandescence when heated. The manufacturing process for mantles was itself a marvel of industrial chemistry. Cotton mesh was soaked in solutions containing the appropriate metallic salts, then carefully dried and shaped. When first ignited, the organic cotton burned away, leaving behind a fragile but functional oxide structure. This delicate object could then glow brilliantly for hundreds of hours before requiring replacement. The streets of Paris, Berlin, and New York soon glowed with this improved technology. Photographs from the 1890s show city centers illuminated with a brilliance that seems almost modern. These images sometimes circulate online with claims that such lighting could not have been achieved through mere combustion. The reality is far more interesting than any conspiracy. Engineers of the era had developed an incredibly refined understanding of how different materials responded to heat, how gas could be purified to burn cleanly, and how reflectors could multiply the effective brightness of any flame. They published their findings in technical journals available to anyone who cared to read them. Reflector technology itself represented another area of sophisticated development. Polished metal surfaces behind flames could redirect light that would otherwise be lost into darkness. Parabolic reflectors concentrated light into beams for searchlights and stage lighting. Spherical reflectors spread illumination more evenly for general area lighting. The mathematics of reflection had been understood since ancient times, but Victorian engineers applied these principles with new precision and purpose. They calculated optimal reflector shapes for different applications and developed manufacturing techniques to produce surfaces of appropriate smoothness and accuracy. The infrastructure supporting these lamps represented another triumph of 19th-century engineering. Gasworks were constructed on the outskirts of major cities, where coal was processed in massive retorts. These facilities operated around the clock, converting thousands of tons of coal into gas each year. The raw gas contained impurities that had to be removed before distribution. Tar condensed in cooling pipes and was collected for sale as a valuable byproduct. Ammonia was absorbed by passing the gas through water or chemical solutions. Sulfur compounds were removed using beds of iron oxide that could be regenerated and reused. The purified gas was then stored in enormous holders called gasometers, which used water seals to maintain pressure. These distinctive structures became landmarks in cities around the world. Their design was elegant in its simplicity. A large tank of gas floated within a larger tank of water, rising and falling as gas was added or withdrawn. The water seal prevented leakage while allowing the holder to accommodate changing volumes. Pressure remained relatively constant regardless of how full the holder was, simplifying the task of distributing gas at consistent rates throughout the network. A network of mains and service pipes distributed this gas throughout the urban area. Main pipes ran beneath major streets, with smaller service pipes branching off to individual buildings and lamp posts. The pressure had to be carefully regulated to ensure consistent flame size at every lamp. This required pressure governors, safety valves, and constant monitoring by trained workers who patrolled their districts looking for signs of problems. Leaks could be detected by smell, since coal gas contained sulfur compounds with distinctive odors. This was actually a safety feature, making gas leaks noticeable before dangerous concentrations could build up. The lamplighters themselves became iconic figures of the Victorian streetscape. They worked according to precise schedules, lighting lamps at dusk and extinguishing them at dawn. Each carried a ladder and a long brass pole tipped with a small flame. Their routes were carefully planned to minimize wasted time while ensuring every lamp received attention at the appropriate hour. In London alone, thousands of gas lamps required nightly attention. This was a labor-intensive system, but it worked remarkably well for its era. The lamplighter was not a keeper of mysterious technology. He was a municipal employee doing a job that required reliability and attention to detail rather than esoteric knowledge. Training programs for lamplighters covered the practical aspects of their work in considerable detail. They learned to identify common problems such as clogged burners, damaged mantles, and broken glass. They carried basic tools and replacement parts for minor repairs. More serious issues were reported to maintenance crews who handled specialized equipment. The entire system operated with military precision, ensuring that city streets remained illuminated throughout the hours of darkness when crime and accident were most likely. Some theories propose that these lamps actually operated on electrical principles, drawing power from an atmospheric source or from hidden generators beneath the streets. Proponents of these ideas point to certain decorative elements on lamp posts, suggesting they might have been antennas or receivers of some kind. However, detailed examination of surviving 19th-century lamps reveals no electrical components whatsoever. The internal mechanisms are purely combustion-based. Gas inlet valves, burner assemblies, and ventilation channels can all be traced in original designs and in lamps preserved in museums around the world. The decorative elements are simply that, decorations reflecting the aesthetic preferences of their era. The confusion may arise partly from the overlapping timeline of gas and electric lighting. By the 1880s, arc lamps and incandescent bulbs were beginning to appear in select locations. The Paris Opera House installed electric lighting in 1881. London's Savoy Theatre followed soon after. These early electrical installations were genuinely impressive, and they sometimes operated alongside existing gas infrastructure. Photographs from this transitional period can be misleading if the viewer does not understand what they are looking at. A street might have gas lamps on one block and experimental electric lights on the next, with no visible difference in the quality of illumination. Arc lamps deserve particular attention as a transitional technology between gas and incandescent electric lighting. These devices created brilliant light by maintaining an electrical discharge between two carbon electrodes. The light produced was intense but harsh, suitable for street lighting and industrial applications rather than domestic use. Arc lamps required constant adjustment as the carbon electrodes burned away, and early models needed frequent attention from operators. Automatic feed mechanisms were developed to address this limitation, but arc lighting never achieved the convenience of either gas or incandescent technology. Thomas Edison's development of a practical incandescent bulb in 1879 marked a turning point, but the transition from gas to electricity took decades. Gas lighting remained dominant in many cities well into the 20th century. The two technologies coexisted, each with advantages and disadvantages. Gas was cheaper to install in areas already served by mains. Electricity required new infrastructure but offered greater convenience and safety. The gradual nature of this transition means that many historical photographs show a hybrid environment where both technologies were in use simultaneously, sometimes on the same street or even in the same building. The metallurgy of 19th-century lamp fixtures deserves particular attention from anyone seeking to understand the true sophistication of the era. Cast iron was the primary material for lamp posts, chosen for its strength, durability, and relative affordability. Iron foundries developed specialized techniques for producing the elaborate decorative elements that adorned these structures. Floral patterns, scrollwork, and figurative sculptures were all cast using methods refined over centuries of practice. The quality of this work was exceptional, and many original lamp posts remain standing today, testament to the skill of Victorian craftsmen who took pride in their creations. The casting process itself was a marvel of controlled metallurgy. Molten iron had to be poured at precisely the right temperature to fill intricate molds without creating defects. Cooling rates affected the final properties of the metal, determining whether it would be brittle or tough. Foundry workers developed intuitive understanding of these processes through years of apprenticeship and practice. Their knowledge was practical rather than theoretical, but no less sophisticated for that. They could produce castings of remarkable complexity and consistency without access to modern analytical instruments. Brass and bronze were used for components that required resistance to corrosion and heat. The burner assemblies, valve mechanisms, and decorative trim were often made from these alloys. Their golden color added to the visual appeal of the fixtures while serving practical purposes. These metals could be machined to tight tolerances, allowing for precise control of gas flow through orifices and valves. The craftsmanship required to produce these components was significant, and specialized manufacturers emerged to supply the growing market for gas-fitting hardware. Glass technology also advanced dramatically during this period. The globes and shades that surrounded gas flames were not merely decorative. They served to protect the flame from wind, to diffuse the light for more even illumination, and to reduce glare for pedestrians walking beneath. Different types of glass were developed for different purposes. Frosted glass scattered light more evenly across a wide area. Colored glass could create specific moods or indicate different types of establishments. Cut glass added sparkle and visual interest that complemented the warm glow of gas flames. The glass industry of the 19th century was a sophisticated enterprise, producing materials of remarkable clarity and consistency. Glassmakers understood how to control the chemical composition of their products to achieve specific optical properties. They developed techniques for pressing, blowing, and cutting glass into almost any shape imaginable. The resulting products were not only functional but beautiful, combining technical excellence with artistic vision in ways that continue to inspire admiration today. The theories suggesting that these lamps operated on some form of free energy often point to the lack of visible fuel delivery in certain photographs. However, gas pipes were typically buried underground or concealed within the lamp post itself. The infrastructure was deliberately designed to be unobtrusive, maintaining the aesthetic appeal of city streets while delivering fuel efficiently to every fixture. This concealment was a feature, not evidence of hidden technology. Urban planners and engineers took great pride in creating systems that worked seamlessly without cluttering the visual environment with exposed piping and mechanical equipment. Scientific understanding of combustion advanced significantly during the 19th century, providing the theoretical foundation for practical improvements in lighting technology. Researchers like Michael Faraday investigated the chemistry of flames in meticulous detail. His series of lectures on the chemical history of a candle, delivered at the Royal Institution in 1860, explained the fundamental principles that governed all combustion-based lighting. Faraday demonstrated how fuels vaporized, mixed with air, and underwent chemical reactions that released both heat and light. As he noted, there is no more open door by which you can enter into the study of natural philosophy than by considering the physical phenomena of a candle. The development of specialized fixtures for different applications shows the depth of engineering knowledge available at the time. Indoor lamps were designed differently from outdoor ones, with considerations for ventilation, heat management, and aesthetic integration into interior decor. Reading lamps prioritized brightness and adjustability, allowing users to position light sources for optimal visibility. Chandeliers emphasized decorative impact while providing ambient illumination for large rooms. Street lamps needed to withstand weather and resist tampering while providing reliable illumination night after night. Each category required specific solutions to unique challenges. Factory lighting presented particular challenges that spurred innovation. Industrial spaces required illumination that was bright enough for detailed work, safe enough to use near flammable materials, and economical enough to operate for extended hours without excessive fuel costs. Solutions included enclosed flames with safety mesh that prevented ignition of explosive atmospheres, forced air systems that improved combustion efficiency by delivering precisely controlled quantities of oxygen, and reflective housings that directed light where it was needed while minimizing waste. These developments emerged from practical experimentation and careful observation of what worked and what did not. Mining operations required even more specialized lighting solutions. Open flames in underground mines could ignite explosive mixtures of methane and air with catastrophic results. The Davy lamp, invented by Sir Humphrey Davy in 1815, addressed this danger with a fine metal mesh surrounding the flame. The mesh allowed air to pass through for combustion while preventing the flame from igniting gases outside the lamp. This invention saved countless lives and demonstrated how scientific understanding could be applied to solve deadly practical problems. It also showed that Victorian engineers took safety seriously and developed sophisticated solutions when circumstances demanded. The regulatory environment of the 19th century also shaped lamp technology in important ways. Concerns about fire safety led to mandatory standards for gas installations in buildings. Insurance companies required compliance with specific codes before they would underwrite commercial buildings. Municipal authorities established inspection regimes to ensure public safety. These regulations drove improvements in design and installation practices while creating documentation that survives in archives today, providing detailed records of how gas lighting systems actually worked in practice. Economic factors influenced the spread and development of gas lighting in ways that are sometimes overlooked by those focused on technical aspects alone. The cost of coal, the expense of laying pipes, the wages of lamplighters, and the price that consumers would pay for light all affected business decisions. Improvements in technology were often driven by the desire to reduce costs rather than by pure scientific curiosity. The Welsbach mantle succeeded partly because it dramatically reduced gas consumption while increasing brightness, making gas lighting economically competitive with the emerging electrical alternative for another generation. The aesthetic preferences of the Victorian era also left their mark on lamp design in ways that continue to influence urban furniture today. The prevailing taste favored ornate decoration, historical references, and displays of craftsmanship. Lamp posts became opportunities for artistic expression as well as functional infrastructure. Different cities developed distinctive styles that reflected local culture and manufacturing capabilities. Paris favored elegant Art Nouveau curves. London preferred classical motifs and heraldic symbols. American cities often chose designs that proclaimed civic ambition and technological progress. By the turn of the 20th century, the age of gas lighting was clearly waning. Electric utilities expanded rapidly, offering light that was cleaner, safer, and more convenient. The infrastructure that had seemed so modern just decades earlier began to appear obsolete. Many gas lamps were converted to electric operation, their original burners replaced with sockets and bulbs. Others were simply removed as streets were modernized. The transition was sometimes nostalgic, with newspaper editorials lamenting the passing of the familiar gaslit streetscape that had defined urban nights for nearly a century. Some gas lamps survived, preserved as historical curiosities or maintained in districts where their atmospheric quality was valued. Cities like London, Prague, and Berlin still operate small numbers of working gas lamps, tended by modern lamplighters who carry on an ancient tradition. These surviving examples offer tangible evidence of how the technology actually worked. Anyone who doubts that gas lamps operated on combustion principles can visit these locations and observe the process directly. The flames burn just as they did in Victorian times, fed by the same basic chemistry that Murdoch discovered more than 2 centuries ago. The persistence of alternative theories about 19th-century lighting reflects broader patterns in how people engage with history. Complex infrastructure that works invisibly can seem almost magical to those who do not understand its operation. The Victorians themselves might be amused to learn that their gas lamps are now the subject of speculation about lost technology. They saw themselves as participants in an age of progress, applying scientific knowledge to practical problems in ways that transformed daily life. Their achievements were remarkable precisely because they were grounded in real understanding of how the physical world worked. Modern materials science and engineering allow us to analyze surviving lamps in extraordinary detail. Spectroscopic analysis can determine the composition of alloys used in burners and fittings. Metallographic examination reveals manufacturing techniques and quality control practices. Chemical residues in old burner assemblies confirm the types of gas that were used and the temperatures at which they burned. This evidence consistently supports the conventional understanding of 19th-century lighting technology. There are no mysterious compounds, no inexplicable components, no signs of energy sources unknown to science. The documentary record from the period is equally consistent and remarkably comprehensive. Patents describe gas lighting technology in exhaustive detail, including diagrams that show every component and its function. Technical journals published articles on improvements and innovations, debating the merits of different approaches. Manufacturers produced catalogs showing their complete product lines with specifications and prices. Municipal records document the installation and maintenance of street lighting systems with bureaucratic thoroughness. This paper trail creates a comprehensive picture of an industry that was thoroughly understood by its participants and openly discussed in public forums. What remains most impressive about 19th-century lighting is not any imagined mystery but the genuine ingenuity of the engineers who developed it. They worked with the materials and knowledge available to them, solving problems through experimentation and careful reasoning. The lamps they created illuminated streets, homes, and factories across the industrializing world. They transformed urban life, extended productive hours, and created new possibilities for commerce and culture. This legacy deserves recognition on its own terms, without embellishment by unfounded speculation. The warm glow of a gas lamp still evokes a particular mood, a connection to an era that seems both distant and strangely familiar. Standing beneath one of the surviving fixtures on a quiet evening, an observer might feel transported to another time. The flame flickers and dances just as it did for Victorian pedestrians. The shadows fall in patterns unchanged across more than a century. But this atmospheric experience does not require belief in lost technology to be meaningful. The lamp is impressive enough as a product of human creativity, scientific understanding, and skilled craftsmanship. It needs no mysterious origin to deserve admiration and study. The real story of 19th-century lighting is ultimately more fascinating than any alternative theory could hope to be. It involves dedicated researchers who spent years understanding combustion chemistry. It includes entrepreneurs who saw commercial opportunities in new technology and risked their fortunes to build infrastructure. It encompasses the laborers who laid miles of pipe beneath city streets in dangerous and exhausting work. It celebrates the lamplighters who made their rounds in all weather, ensuring that cities remained illuminated. It reflects the aspirations of an age that believed in progress through applied knowledge and collective effort. This story connects directly to our present, where the infrastructure that illuminates modern cities still depends on the same principles of engineering and organized effort that the Victorians pioneered. The electric grid that powers contemporary lighting evolved directly from the gas networks that preceded it. The same organizational structures, the same regulatory frameworks, the same economic models continue to shape how cities provide illumination to their residents. Understanding this continuity provides perspective on both history and the present moment. As evening falls on a 21st-century city, electric lights flicker on automatically, controlled by timers and sensors that the Victorians would have found magical. The direct descendants of those 19th-century innovations continue to shape daily life in ways that most people never consider. The continuity between past and present is unbroken, a chain of development and improvement stretching back through generations of engineers and workers who each contributed their part. The lamps of the 1800s were not relics of a lost civilization. They were products of a civilization in the midst of transformation, learning as it went, building the foundations of the modern world that we inhabit today.